Hello, everyone. We're working through chapter 14, part 1, ANOVA for completely randomized designs. This is to accompany an introduction to statistical methods and data analysis by Ott and Longnecker. All right. In a completely randomized design with a single factor, our goal is to compare T different population or treatment means. We're going to assume there are T different populations that we are studying, and from there, every single sample size to go along with those T different populations will be denoted with N1 down to NT. Okay, so we can think of our treatment going from 1 to T, and then our observations will be Y11, that's the first person and the first treatment. Y12 is treatment 1 and the second person, all the way up to Y1N1, which is the N1 person taking treatment 1. And then if you go to the T treatment, you have YT1, which is the first person under the teeth treatment. YT2 is the second person under the teeth treatment. And then YTN sub T would be the response for the teeth treatment and the in-teeth person within that treatment. All right, for each of these treatments, we could calculate a y bar 1 dot all the way down to a y bar t dot, which is calculating the sample mean of the response for the T different treatments. All right, so in a completely randomized design, we can think of having the model be set by Yij equals mu I plus epsilon ij. Okay, so the mu I is the ith treatment mean, right? And the Yij is the observation of the jth experimental unit receiving treatment I. Or if we were dealing with people, that would be the jth person receiving treatment I. Okay, we could further decompose this mu I to be mu plus tau I, where mu itself is the overall treatment mean, and tau sub I is the effect due to treatment I. Okay, so whether or not you could essentially set your model up to be Yij equals mu I plus epsilon ij, or you could say Yij is equal to some overall mean plus the treatment effect tau I plus epsilon ij, right? These two models are equivalent. Okay, so remember your epsilon ij is your random error associated with the response from the jth experimental unit receiving treatment I. And those epsilon ij's are independent and they are distributed as normal random variables with mean 0 and variance sigma squared epsilon. So if we wanted to, we could say, okay, what's the expected value of Yij? Well, that's the expected value of mu I plus epsilon ij, which is the same as the expected value of mu plus tau I plus epsilon ij. And we can pull that expected value through this linear combination, expected value mu plus the expected value of tau I plus the expected value of epsilon ij. Well, remember that mu is an unknown constant, so the expected value of mu should just be mu. And then the expected value of tau I, once again, that's an unknown constant, that'll be tau I. Then the expected value of this epsilon ij equals 0. So when we're talking about our expected value of Yij, we just get our mu plus tau I. Now, if we want the variance of Yij, then that's going to be the variance of mu I plus epsilon ij, which is the same as the variance of mu plus tau I plus epsilon ij. And we can pull the variance through, but since these are independent, right, our mu and our tau I should be independent of the epsilon ij. So we end up just getting that this is the variance of mu plus the variance of tau I plus the variance of epsilon ij. Well, since mu is an unknown constant, the variance is 0. Since tau I is an unknown constant, then the variance is 0, and all we're left with is the variance of epsilon ij, and that we already know from the model of assumptions that should be sigma squared epsilon. So now from these assumptions, we get the final distribution of Yij being independent and identically distributed normal random variables with a mean mu plus tau I and a variance of sigma squared epsilon. All right. So we're going to go through a lot of notation in the beginning, but it's very important that you become familiar with what the notation means and how to do these calculations. You can have the formulas when you're working on this, but it's more for interpretation. Yij, right? We would say that's the jth observation under treatment I. So for example, if I have 10 treatments, right? Then, and within those treatment groups, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, within those treatment groups, I have a certain number of people or observations within those treatment groups. So suppose for the first group, I had 20 people, and the second group, I had 30 people, and so on. And the 10th group, I had 25 people, right? So each of those treatments has a different number of observations. If I say, what is the Y2, 3 observation, right? That would be the third person, and I should say the response from the third person from treatment 2. Okay. Now, Y bar I dot, that is the sample mean for the ith treatment. So if I took all of these 20 observations and I calculated the Y bar 1 dot, that would be the mean of these 20 people. If I got the Y bar 2 dot, that would be the mean of these 30 people. And I could keep getting all the individual treatment means. I could get the Y bar 10 dot. That is the mean for the sample mean for the 10th treatment, right? So that's what our Y bar I dots are. Our Y bar dot dots, right? Y bar dot dots is if you took every single person under all these treatments and you calculated their mean. It's the overall sample mean. So we get the formula here. And essentially, by setting up the model in this way, we can get estimates of the parameters of the model we were looking at before, right? So if we have the model Yij equals mu plus tau I plus epsilon ij, right? then we could get an estimate for mu, right? We could get mu hat, we could get tau hat I, and from there, you could also get the mu I hats if you were using the model Yij equals mu I plus epsilon ij, right? So overall, by setting up the completely randomized design in this way, you can be able to compare these T different treatments. And after you set up those T different treatments, you might also want to calculate residuals. Well, this is very similar to our regular linear model, right? Our residuals are our observed values, in this case, the Yij's, right? And then minus the predicted values. And all we're doing here is we're taking our basic first principle that a residual is the observation minus the prediction. And now we're just plugging in the particular scenario of a completely randomized design. So we're plugging in the scenario where our observed response for the jth person in the ith treatment is that Yij, and then you're going to subtract off the predicted value, and that's going to give you the residual. So far with the completely randomized design, we see that there's a lot of notation, but once you get into it, the actual coding of it is very straightforward because you're going to just be able to use the LM function in R. And the basic principles of linear regression holds true, but more it's about the setup of the type of design that you have. So in this completely randomized design, right, you start with all your subjects and essentially they get randomized into these T different treatments, right? Treatment 1 all the way down to treatment T. And then you're going to observe the response for each person, Yij. And you're going to be able to set the model up to be able to estimate the effects of each of these treatments when you're in a completely randomized design. So I hope you learned something today, and I'll see you next time.